Hey, I'm Lakshay and I'll be going through our assignment 2 for applied machine learning. To begin, we just import our basic functions and libraries and modules, and we also get our file path and name it as a variable called file name. Then we just read the CVS and name that as a variable as iris, our data set. We get the first 5 rows using head, and then we convert the species name from strings to integers just so our model can work much more easier, as there'll be numerical values instead of it having strings and just having a harder time to learn. And then when we print head, we see the species are integers instead of string values. Here we could assign x to the first 4 columns and y to the last 4 columns. And here we could just do our training testing split for 20% of the data, and we put the random state as 1, 2, 3, so we have a reproducible testing source. And then we could get the head for x train, x test, and y train, and y head. And you can notice the data type being integers. This just confirms that they're transformed in from string to integers. And we could also see the length. The length is 120 for the train and 30 for the test, so just make sure that we're doing our 20% split too. Here we just convert our categorical into one-hot encoded values. After that, we'll define a sequential model. First, we have 100 hidden units. Then we're using our ReLU activation function, and we're just describing the shape of the model. And then here we have, for our second layer, another 100 units, hidden units, and then we're using ReLU again. And then finally, we're using a softback function, and we're using 3 hidden units at the final layer because we want to pick between these 3 species of flowers. Then we compile our model. We're using the RMS prop optimizer, categorical cross empathy for the loss, and we're just having a metrics for accuracy. And we could see as we compile the model, loss goes lower, and then it kind of plateaus over here, kind of jumps back and forth. But our accuracy does go forward. Now we could evaluate the model, and we could see after we evaluated the model, we get our test score, which is test loss, which is 20%, and our accuracy being 86%. And then now we repeat this offset for the first and second hidden layer. We're only going to use 10 hidden units instead of 100 like we did before. So we do that, basically repeating the same steps. And for the epochs and batch size, we're using only 4 and a batch of 10. Previously, we used 20 epochs and a batch size of 10. Here, we're using only 4 epochs. So the model doesn't have as much time to train, and not as many hidden units this time. And we could see this affects the model's loss. It has a higher loss. We always want our loss to converge and go lower. And our test score is not as high as our first model. And it goes into question 10a. The number of layers and hidden units could impact the accuracy of our model. This is because when we have less hidden units and layers, our model becomes less complex, and the neural network can't easily detect any of the hidden patterns that would be in the data. So the more hidden units or layers we have, essentially the more easier it is for our model to recognize the hidden patterns and the complexity of the model itself. Now, do we always suffer from overfitting? No, this isn't true always. It depends on the model and the data itself. Sometimes if we're using a small data set and we do a lot of epochs and use a lot of hidden units, then we might suffer for overfitting. And this might be an example of the first model. how it has 86%. It's not too high, but let's say if we did 100 epochs, then it would be more so overfitting. How can we detect overfitting? So we could detect overfitting by looking at the test accuracy and looking at the train split test as well, and when we use evaluating the model. So we look at our training accuracy, we look at our test accuracy, and we look how the model works in terms of testing. Is it getting the test accuracy lower than the training accuracy? That might be a sign we overfit the model because it's not able to recognize the new testing data that we're giving it. And we could reduce overfitting by reducing the complexity of the model. We could train it for fewer epochs, use more training data. We could also use like regularization or like normalization, where we normalize the data that we use so our model's not all over the place in terms of the features it's using. Here we're just trying different settings for models for 10B. So in the first one, instead of using RSM prop, we used as the optimizer, we're going to use Atom as the optimizer. So we could see the results there. And then for the second one model that we're trying out, we're going to add another hidden layer, see how that works. Then we'll try 64 hidden units instead of 10, see how that affects the model. We'll change the number of epochs to 20 instead of 4. And then we'll try changing the batch size. And here you essentially get a list of summary across everything. It's better at the bottom to see it. And you could see how each separate change we do affects the model itself. And it looks like the best change to get a higher accuracy was definitely the hidden units. When we add more hidden units, this was probably because the model can see more complex patterns within our data due to the more amount of hidden units it gets. Although this could be a sign of overfitting, so we would have to test this out in terms of data it hasn't seen even more. But yes, that's assignment 2.